Hello, everyone. My name is Doxa, and today my teammates and I will be presenting on Centroid-based clustering. My team is made up of myself, Jason, Joseph, and Sharuth. Today, for our presentation, we'll be giving a brief introduction of what clustering is, what central-based clustering is, what k-means are, the different types of k-means, and then our analysis, and then a conclusion. So to get right into it, what is clustering? So clustering is basically a widely used unsupervised machine learning technique that enables groupings of similar data points based on inherent characteristics. And it does this by kind of just grouping based on similarities. And it is used in data mining as well as machine learning, other various domains. Some of the domains that have this has been used in is e-commerce, health sciences, very many different areas where data can be easily grouped based on likings and similarities. So what is central-based clustering? Central-based clustering essentially employs central points known as centroids to group similar data points and basically to give an insight into the data's underlying patterns, right? And so a algorithm that employs centroids is k-means algorithms, which it often is used in centroid-based clustering algorithms. And essentially what that algorithm is, it's an iterative algorithm that aims to minimize the total sum of the distance between the data points and their corresponding centroids. And so for our project, we looked at three different distinct k-means clustering algorithms. We looked at the Lloyd's, the McQueen's, and the Harrogitarian-Wong, and we used these three algorithms, and we come on the Iris dataset. The Iris dataset is a popular dataset about flower petals and its groupings. Um, and so we aim to basically leverage these k-means clusterings and to explore this data set and compare the results with the true labels and evaluate how well the clustering aligns with the actual label set. Just to give a brief overview of these k-means algorithms, and my teammates will go into a little bit of an in-depth explanation of what these are and our analysis and our findings. So for these algorithms, the Lloyd's algorithm selects a k data point as a centroid and then iteratively assigns all data points to their closest centroid, recalculating the centroid as a means to basically assign the data points until convergence, whereas the McQueen's updates the centroids whenever a data point is reassigned, which results in a better assignment with more computation time. And last but not the least, the Hereditary Wong initially assigns all the data points a random centroid. The centroids are then calculated as a mean of their assigned data point, making them initially close together. From here on, my teammates are going to talk about these individual algorithms and how best it compared to the Iris data set and give our analysis on that. Thank you guys so much for listening, and I hope you enjoy our presentation. Thank you.
So on to the procedure. So Lloyd's algorithm is the standard k-means algorithm where data is separated into k distinct groups or clusters. The goal of the algorithm is to minimize the sum of squared distances between each data point and its assigned cluster centroid. Here we have pseudocode describing how the algorithm is implemented. The algorithm starts by choosing k as the number of centroids and then randomly assigns all points to a centroid. Centroids are then recalculated as the means of the assigned points. Next, we repeat the following two steps until convergence. First is the assignment step, and second is the update step. In the assignment step, each data point is assigned to the nearest centroid, and in the update step, the centroids are recalculated as the mean of the data points assigned to each cluster. This process continues iteratively until the centroids converge. In this project, we sought to apply this algorithm to a data set and test to see the results. In this case, we utilized the Iris dataset. In the Iris dataset, there are three classes each point belongs to: Setosa, Versicolor, and Virginica. Because we already knew there were three true classes, we can initialize k to three clusters. After implementation of the algorithm, the figure shown on the slide indicates where the final cluster centers were and to which clusters and classification each data point belonged to. It can be seen that the cluster on the left is fairly well separated from the other two clusters that are more to the middle of the graph. The two clusters that are closer together also show some mixing where the true classes are misclassified into the wrong cluster. This can be further shown with other metrics. So here are those other metrics where first on the left, we have a confusion matrix detailing the number of correct and incorrect predictions, while the Setosa and versicolor classes have an extremely high number of true positives as indicated by the dark blue. The algorithm falsely places a small amount of versicolor data points into the Virginica cluster. The Virginica class, on the other hand, has a lesser amount of true positives with a fair amount of Virginica data points being incorrectly placed into the versicolor cluster. Second, on the right, we have a number of other metrics that give us more insight into the results of Lloyd's algorithm on this data set. First, an adjusted RAND score of 0.7302 indicates reasonable alignment with the true class labels. We also have cluster accuracies for each cluster, which varied. Cluster 1 achieved 100% accuracy, while cluster 2 and 3 achieved 77.42% and 94.74%, respectively. The next three metrics, homogeneity, completeness, and V-measure, were all around 0.75, demonstrating a good balance between cluster purity and class coverage. Lastly, the silhouette score of 0.5528 indicated reasonably well-separated clusters with some overlap. However, this metric is much lower than the other scores, indicating many points may have been close to the decision boundary. Overall, the results show that Lloyd's algorithm performed well, effectively capturing the general structure of the iris dataset and providing meaningful cluster assignments. However, there is room for improvement, illustrated both by the confusion matrix, which isn't 100% accurate, and the silhouette score. This is why we next explore additional clustering algorithms and finally compare those results.
K-mean is one of the simplest and unsupervised learning algorithm that can be solved to the clustering problem. The procedure can be as follows. So first we're going to choose the number of clusters. The first step is to going to define k numbers of clusters in which we will going to group the data. So in this case, let's select the number 4, and then we're going to initialize the centroids. Centroid is the center of a cluster, but the exactly center of a data point is unknown. So we're going to select random data points and define them as the centroid for each cluster. We will initialize 4 centroids in this database. And then we're going to assign the data points to the nearest clusters. In these steps, we will first going to calculate the distance between the data points to the centroid and then use the Ukrainian distance metric. And then we're going to reinitialize the centroid by calculating the average of all the data points of that particular cluster. And then lastly, we're going to repeat the steps 3 and 4. We'll keep repeating until we have the optimal centroids, and then the assignment of data points to the correct cluster are not going to change anymore. So in this case, we can see that in the following example, the McQueen does find very good assignments with the first iterations over all the data points. The second iteration is only just a result of a small quantities of the first assignment. This behavior is typically for McQueen k-means. And then here it's the implementations for the McQueen k-means. First, we're going to find out the distance between the data points and the centroid. And then we're going to assign the data points based on the distance to the closest centroids. And then lastly, here it's the visualizations of the result.
Hey guys, I'm Sushruth and I'm gonna present this part of the analysis, which is the Hartigan Wong k-means, which is an extension of the traditional k-means algorithm because it's an improvement of the previous Lloyd's and the other McQueen's algorithm, where we try to fix the initial random cluster selection by using some sophisticated methods to initialize the centroids. So the algorithm is as such. So basically, we initialize k cluster points randomly, and then we assign each point to the nearest centroid based on the Euclidean distance, which is a formula to calculate distance between 2 points in the space. And then for each cluster, we'll calculate the total sum of squared distances from the data points to the respective centroids, which is going to be an entire sum of all the distances. And then for each data point, we're going to consider reassigning it to k clusters and calculate the change in the total sum of the square distances. For reassignment, this is called as criterion for improvement. And if the criterion for improvement is positive, then we reassign the data points to that cluster, which resulted in maximum improvement. Otherwise, we leave the data point as it is. So the points 3 to 5 are repeated until there are no further changes in the uh, assignments of the clusters. So this is the code that does the job. And so basically we initially we just assign uh, we take first the number of clusters as k, which we have used as 3 here because there are 3 uh, classes that we've used in our data set of the iris data set. And then basically we iterate through each data point and we iterate through each cluster, and we calculate the Euclidean distance. Now we calculate the difference in the Euclidean distance as a means of improvement. And if the difference in the Euclidean distance is positive, then we update the assignment of the cluster to the new cluster where the improvement is positive. We run this until either there are no further improvements or it reaches the maximum iteration limit of 100. So we ran this on the iris dataset, which is basically a very popular dataset in the data science community. And we calculated the metrics on a few different parameters, like the cluster accuracy. This is basically how accurately a point is being classified into the cluster. So we've got an accuracy of 0.79 for this particular type of k-means, which is close to 80%. And homogeneity, which means how true are the assignments to the clusters, which is about 75% here. And adjusted rand score, which is about 73% here. Also, we plotted all the different labels and their classifications with the centroids. So the cross mark on the right side is a graph. The cross mark denotes the centroids, and there are 3 colored points, which is the yellow, purple, and blue, which is of different labels. Yellow is for Setosa label of the iris dataset, and versicolor is of purple, and virginica is for the cyan color. So according to this, we can see that there's a pretty decent clustering, and but there are some interferences in the 2 clusters of yellow and purple color. Yes, that's about my part for the presentation.
So, in conclusion, we were able to describe the 3 main ways that we implement centroid clustering, and these include the Lloyd algorithm, the McQueen's algorithm, and the Hartigan-Wong algorithm. While they all use centroids for clustering, they have different implementations that they use that we were able to get into. So, some of the main takeaways when performing these algorithms on the iris dataset is that all 3 algorithms performed within the same ballpark on the iris dataset, being pretty successful with accuracies around 70%. And this indicates that either the dataset was too simple to really show the differences in the algorithm's performance, or that the algorithms themselves are just very similar. And since they are all the other two, the McQueen's and the Hartigan-Wong are variations of the Lloyd algorithm, it does make sense that they would perform similarly, which we discovered when actually looking and implementing these algorithms within Python. So other algorithms that veer further from the standard Lloyd's algorithm could be explored in the future to really compare the nuances between various algorithms that utilize centroid clustering. So those are the main takeaways. We hope that you enjoyed this presentation and that you'll a little more excited about centroid clustering than before. So yeah.